Hello, my name's James Claffey, presenting with Logan DeWitt. This is our Purdue University COVID-19 Innovation Challenge project presentation. First of all, I'd like to take a moment to apologize for the strange presentation format. In an effort to keep with the theme of the project and social distance, Logan and I are not presenting together, so each of us will present separate slides for this presentation.
Hi, my name is Logan DeWitt. James and I are both going to be seniors in mechanical engineering this coming fall. When we heard about the challenge, we immediately felt like we could help. We are excited to go back to campus in the fall and would love to see Purdue return safely.
After conducting some research, Logan and I found that the second most common method of virus transmission is through surface interaction. There's also been some research that shows that the virus that causes COVID-19 can live on surfaces made out of plastics and stainless steel for up to 3 days, and stainless steel is actually what most of the door handles around Purdue are made out of. Finally, according to the American Journal for Infection Control, the average student touches their face about 23 times per hour. So our solution is not to eliminate the subconscious act of touching your face, but to eliminate the conscious act of direct contact with things like door handles and railings. The device that Logan and I have come up with is the Protect Purdue Contactless device, or the PPCD, and it's basically a tool to avoid direct contact with both push and pull doors, railings, and bus support bars. Our model uses a low weight, low cost, high strength aluminum material that is easy to manufacture. Our plan is also to make this convenient to carry around campus with an extension device that can clip onto a backpack or a purse for easy access. The device will also be hand washable in case it needs to be cleaned after use.
When designing this device, we investigated the function of opening and closing doors on campus. As stated by the Americans with Disabilities Act, an exterior door should require a maximum of 10 pounds of force to open it and 5 pounds of force for interior doors. While this is their standard, in real life this does not account for the joking motion people typically use to open doors. To account for this, we applied a factor of safety of 3 to the force to ensure our design is applicable for all doors on campus. The pictures on the right display simulations of the motion of pulling and pushing and have a color map to show where the most amount of stress occurs. On the keys, we can see the minimum factor of safety for these simulations is 5, which means this device is able to withstand 5 times more than the 30 pounds of force that is applied. In order to prove our device is more than capable, we determined that when the device is made out of aluminum, it can withstand a pulling force of over 150 pounds. This could be applicable when riding a bus and there is a sudden jerk and someone needs to really hang on. Our device could help prevent so many people from touching the handrails in a bus, for an example. The picture above shows the color map and the key to the left of it of how we're able to withstand 150 pounds. As an example of the device, we've 3D printed the PPCD. This plastic version is very strong, but to withstand consistent everyday use, we believe that making the device out of metal would be more suitable, as our stress calculations suggest. We then made a plaster mold of the device, shown here on the right. I was able to cast the device in recycled metal using the process displayed here. First, I smelted down aluminum cans into ingots. I then remelted the ingots and poured them into the hardened plastic mold. In the fifth picture, you can see the rough forged device that came out of the mold. After some sanding, I was able to successfully cast the once plastic device into an aluminum model. This process displays how we were able to think of a solution and work towards a functioning prototype. James will later expand on the implementation of this process and how it will be an innovative and practical device for the Purdue population.
This is one concept already on the market that Logan and I found, but we decided that there were improvements that we could make to the design to make it more viable. First, it has a small lever arm, which makes it more difficult to open doors, especially some of the heavier doors I know we have all experienced around campus. Second, it has lower strength tolerances than our design due to thinner edges and less surface area for the hand. Next, it's really only useful for pull doors and doors with handles, while ours can be used for push doors as well. And then lastly, it has no gripping mechanic, so it could frequently slide off of handles during use. The manufacturing process that we came up with was to use the water jet cutter that's located in the Bechtel Innovation and Design Center on Purdue's campus to cut our part out of aluminum plate sheets and then to sand or grind down any imperfections on our piece and then just to drill the carabiner attachment hole. We performed a cost analysis on it and found an aluminum plate 5 by 10 feet on a website that is sold for about $500. And then we calculated that we could fit about 264 pieces onto this plate, which comes out to be about $1.90 per piece, which is extremely affordable. An alternative manufacturing process that we believe could be viable is the investment casting process that Logan described earlier, which actually will produce a stronger piece and requires no secondary machining. So we did a cost analysis for this as well and found an online investment casting calculator and put in the dimensions of our piece and found that producing 20,000 parts would cost about $2.25 per piece, and then 40,000 parts would cost about $1.59 per piece, which are both still very affordable. And then IQE Casting, which is located in Indianapolis, provides this service.
We appreciate you taking the time to listen to our presentation. We believe our idea is innovative and displays a practical way to help prevent the spread of COVID-19 on our campus. As always, boiler up and hammer down.